Thank you very much for that wonderful introduction. No? So, good afternoon, everyone. No? So, thank you very much no, for coming here no, at Pardo Hall. No? So, actually, this is my first time attending and even speaking at this type of conference. No? So, hopefully, you can learn something from this talk. No? So, for today, we'll talk about Python and structures, Python in the structural engineering industry. No? So here's an overview. So my talk has 6 parts. So first, I'll talk about what I do or what we do as structural engineers, no? And what are the things that we do, what are the workflows that we do in the analysis and design of structures, no? And then I'll mention some disadvantages no, when we do such workflow. And then from there, I'll introduce you to the API or the application programming interfaces that are being used in structural engineering, as well as the libraries that we use in structural design. No? Since structural software use the concept called finite element analysis at its base, and so there are Python libraries that can do finite element analysis. So I'll enumerate some of them. And from there, I'll mention some specific miscellaneous examples of that do not use the libraries, no? Standard data science libraries. Okay. So some short introduction. So I'm a structural engineer by profession, no? But highlighted at the bottom, so I'm also a part of the Python team for the Association of Structural Engineers of the Philippines. Just last year, we conducted a seminar to structural engineers no, on the use of Python, especially beginning structural engineers, on the use of Python and how they can apply them to their workflows no, in design and analysis of structures. No. So before we go anything else, no, let's, of course, what do we do no, as a structural engineer? No? So I show here 2 pictures. No? So one is from the flooding in Florida, and to the left, that's to the left, and to the right is after a devastating earthquake in Turkey. I think you have heard that. No? And as you can see here, the rest of the buildings have been like completely devastated, they collapsed, no? But there are 2 structures here that still stands, no? Even with those extreme conditions. No? And we as structural engineers, so we aim, no? We dream, no? We aim that all of the structures will stand like this, no? And so we at the structural engineering industry, no, we design buildings like this or bridges, no, such that they will survive, no, or do not collapse, no, during extreme calamities, no, like earthquakes and wind, typhoons. No. So by definition, no, so structural engineering is an approximate science. No, when you say approximate, no, the material strengths are approximated. The method of idealization from a real structure to a computer model no, is also approximate. The methods of analysis are also approximate. No? But the objective is, while all of those are approximate, no, the resulting design, the resulting structure will be able to survive no, those loadings or those extreme environments. No. So basically, that's what. So it's built to last no, by several years, 50 years, 75, 100. No? So what we do is we idealize a structure, no? Even if it's not built yet. We idealize a structure into what we call a computer model, no, like this. And from the computer model, we analyze it to give us some colorful contours like that, no, which give us numerical values, no, which we can compare with some predefined or pre-approved codes, no, of guidelines for making the structure pass, no, or pass the checks. No. As well as bridges. No. So bridges like this, we also model using a computer model, no, and we analyze it using a computer model. And basically, just to make it short, the process of structural design starts, of course, with a client, no, who has a dream of building something, and then we, as engineers, including the architects, we transform it to a computer model, and then once the computer model is okay, we transform it into drawings, and then from the drawings, we transform it into an actual construction. No? So basically, we design it in an office-type environment, no? And we also refer to several standards, no, or codes, no, such as the NSCP 2015, or even in the American standards like ACI. No? And then, once the drawings are okay, no, we also do some inspections, no, to ensure that the structure is being built as indicated in the drawings. No? So basically, that's what we do as structural engineers. No? Now, next part is, so what is the standard workflow for structural design? So first, we use many proprietary software. So it's a lot here, no. Actually, I am familiar with many of this. No? So now the standard procedure is this one. So we have a model. Basically, we add materials, the strengths of materials. We add the sizes of the beams or the columns or the foundations. We add them, and then we construct the geometry based on what the client or the architect requires, and then add some constraints, no, to make the structure fixed. And then we add the loadings, so that includes loadings from the people inside, from the equipment inside, from wind, and from earthquakes. No? So we included them in the loads. And then we analyze them, and from there we extract results. No? So basically numerical values, which we can compare with the codes. No? So to see if they are okay. You know? And then if there are something that is not yet okay, you know, like the numbers are failing, then we can just revise those beams, we can revise those columns, no? And then we do it iteratively until we get a structure that is not only safe but also economical and sustainable. Now, for an existing model, no, some of these steps are skipped. No? So basically, since we have an existing model, we just go through the analysis directly. And if we have like a third-party software, that we can just import it, no, and then do some stuff, no, like this one, and then we proceed with the analysis. No? Now, the problem with this, by the way, so here's what a structural model looks like, and then we extract the tables, no, and then from the tables we can go to more detail on each, no, to check if there are some parts that the member is failing, or is it okay, is the details okay, and then from there we can convert to drawings, basically. Now, the problem with this is because it requires human intervention. No? So basically, the software, so the typical workflow is from the software, the user exports the tables to Excel and back. And then sometimes more advanced structural engineers use Python, no, to import the Excel file, no, as a data frame, pandas data frame or polars. No? But there's no connection between Python and the software, no? So structural design software. No? And then from the software, we drew the drawings, then we do the reports, no, in MS Word, for example, and then finally, we send the reports along with the drawings to the client, no, or to the architect. Now, the problem with this is it's too many human interventions. No? So it's too time consuming, no? Especially if you need to do many changes. No? So, and it's prone to human error because you need to copy and then import, export, no, from one place to another. No? So it's too time consuming. It's difficult to version control. No? Although companies when they do version control, they save multiple backup files, no, with different version numbers. That's what they do. And then last is because it's too repetitive. No? Sometimes it becomes boring. No? So what if there is a connection between we can directly and we can directly communicate with the design software using Python, no, itself. No? And that's what API is for. No? So I think many of this know this already, but just in short, no. So API is like ordering at a restaurant. So you order a food, no, or like requesting something, and then the server, no, will process it and then give to the API, no, and then the API will deliver the response, no, to you. No? Or if you need to change something, then the API can also do the deletion, no, or the modification. Okay. Now, many proprietary software, commercial software, actually, so they have different, so each of them has API, no? And listed in this table are the Python libraries available for each of the commercial software, no, in the industry. No? So personally, I know how to use the first 5 here. So because we have softwares for this 5. No? But for additional information, no, the libraries for the other 5 are here. No? Okay. So I'll discuss in brief the first 3 software here. So for the ETABS Open API, so ETABS uses a so Microsoft Component Object Model. No? So, and here's a typical flowchart for using the ETABS Open API. So basically, we create an object, a object called ETABS v1 helper, and from there, it can be used to either connect to an existing open file, ETABS file, or create a new file within ETABS. No? And once that file is created, the API will create a CSAP model object, no? And from there, we can now access several methods. No? So methods for creating nodes, methods for setting units, methods for creating beams, columns, methods for analysis, methods for extracting results from there, and then methods for doing automatic design. So like that. No? So all come from a single object, no? The CSAP model object. Yeah. Now, some examples, no. So by the way, in this talk, no, I'll show many examples, no. Some from some designed by me and some designed from my fellow structural engineers. So this one, so models a high-rise structure right here, and then uses the ETABS Open API. So he has a PyCode code here, and then import some libraries like LampPy, Matplotlib, and Pandas. No? And then from there, he can input a table, no, containing the forces, as well as do some post-processing to convert those forces to reinforcements, to the sizes of beams, no, which is available for this one. No? So we can convert to drawings. Another example is from one of my fellow structural engineer. So from an ETABS model, so he obtained, so this is one is called a pile foundation. So if you have seen one, no, in construction, no, basically pile foundations are very deep, like cylinders or even squares, no, that are being put in the ground, no, in order to make the foundation of a building more stable, no, and stronger. No? So basically what he did is imported the reaction forces from an ETABS model, and then use Matplotlib and Shapely libraries to visualize the forces in each of the piles as well as the sizes of each pile. No? So here's the result of that yun. Then there's also one from STAAD, so the OpenSTAAD API. Now the difference being, while in the ETABS Open API, so all methods are being called from a same CSAP model object. No? So the disadvantage is there is no grouping being made. No? So you just call methods from one object. No? But in the OpenSTAAD API, from OpenSTAAD object, you can call other objects from it. No? So you can call objects for unit setting, you can call objects for geometry, you can call objects for analysis, you can call object for design. No? And then from each of those sub-objects, you can call the methods for each. No? So OpenStud API is actually more organized in terms of calling no, yung methods natin. Yeah. And then some examples. No? So this one is from this guy who imported. No? So he has a program that can import stud models, no? And then visualize it here. I think he used a tkinter library to make the GUI. Yeah. And then another one is this. So again, using a tkinter. So this is a bridge design automated modeler and as well as designer. So basically, you create the bridge from the GUI, and then once you, then there is a button that can import the geometry as well as the loading to the STAAD software, like this. So it's an automatic import, no? So complete with the loads, and then you can also analyze it from within, of course, from within the GUI. Yeah. So, and then you can just change the parameters of the bridge, and the bridge will update no, in its appearance as well. And you can import it again to the STAAD software for analysis. No? So basically, it's what we call parametric design. So we design based on certain parameters only. No? And you only need to change that, and the program will do it for you. Yeah. Okay. Now, the third one is, of course, for the MIDAS. No? Now, MIDAS is different because rather than using the comp types library in Python, MIDAS uses a REST API, or RESTful API. So it's a web service. So instead of creating objects, it's communicating via a web service. So we need an API key here. So it's doing a check here. And then from there, we do the HTTP requests method. HTTP request, no, post, put, get, delete. No, so basically, those are the methods no, to be able to create models. Yeah. Now, some examples, of course. So again, my fellow engineer. So while earlier we shown one in ETABS, we also have one here in MIDAS. Here, so piles. Now, another example is this one. So I just made this. So here's, if you are interested on what an API in structural engineering looks like. So here's the Python code. No, you can scan it. No, it will lead you to my GitHub repository. Yeah, so again, you can check the code. No, but basically, the code, what we call that is to model the truss, so roof truss, model the roof truss, analyze it, model, analyze, design it, and even optimize. Now, when you say optimize, we want the design to be not only safe but also cost-effective, as smallest cost as possible. So we do the optimization here. Yeah, and then here are the parameters of the truss. And then here is the workflow of the program. No? So we model the truss, we analyze, we extract the forces, we determine the maximum axial forces. No? Basically, this part is using the Polar's data frame. And then calculate the amount of steel in the truss in kilograms. And then calculate the DCR, no? Or the design to capacity ratio. No? So when you say DCR, when a DCR is less than 1, the structure is considered to be safe, no, or passing the checks. No. But if the DCR is greater than 1, then we can consider that member to fail, no, in the checks. No. And so we need to revise that member. No. And so what the program does is whenever it encounters a DCR greater than 1, then the program will automatically change the sections, no, the sizes of the members in the truss, and then redo the analysis automatically, no, until all of them pass the checks. No? Or even if the quantity of steel is still greater than very large pa. So here, if the difference between the old and the new design is greater than 2% in weight, no, then we need to revise the sections, no, until it's done. No. Now, the end result is actually, I just added this. We can also do some investigations, no, using Python. No. So here, investigated, no, what is the ideal spacing of trusses in roofs. No, you given the configuration. No, and we can see from this graph. No, so it's using matplotlib for the plotting and the scikit-learn library for the linear regression. So what linear regression with linearization, since it's a power equation. So here it can be shown that at around 3 to 4 meters, the quantity of steel is around 40 to 60 kilogram per meter spacing. No? So it's like the ideal spot for the spacing of truss, no? Which is sounds about right, no? For my rules of thumb. So around 3 meters. So yeah. Okay. Next is so as I mentioned earlier, structural engineering software use finite element analysis at its base. No? So what is finite element analysis? No? So I'll do a quick discussion of this. So basically, finite element method is just a numerical method. No? One of the classes of numerical methods for solving differential equations in 2D or 3D. No? So finite element method can be seen in bridge design like this, in structure design like this. No? So we can see vibrations like that. No, even in not in structural engineering, it can be seen in mechanical engineering. No? So for automotive design, no, checking the aerodynamics of cars, even in electronics, no, to check the current within a board, as well as temperatures, no, during operation, no, of like the circuit board. Yeah. So actually, finite element is not just structural engineering, no, other engineering fields as well. Now, basically, finite element method consists of 4 steps. No? So starting with a differential equation, no, the standard form, no, we reduce it to an integral. No? So we reduce it to like this, and then we construct 3 quantities, no, for each of the member in the structure. And from there, we assembled it in matrix form, no? So which gives us this equation. No? So this one is in matrix form, and when you think of matrix, of course, the first library that comes in our mind is the NumPy library, right? So actually, finite element method can be done using NumPy, no, library. So because it has methods for adding matrices, getting the inverse of matrices, getting the eigenvalues. No, it has the libraries for that. No. So basically, what we do is from those equations, no, for each of the member in the structure, we assembled it into a single large matrix, no, called the global stiffness matrix. No. And the way we assemble that is by adding each of them one by one, like this. No. So we add them for each member, no, until we construct the whole matrix, no, which we can solve by solving linear equations. No? So matrix inverse, no, and something. So something that can be done in NumPy. Yeah. Okay. Now, of course, the process, no, of finite element method is the same as what do you call this? It's the same as with proprietary software. No? So we model, and then we analyze it, no, and the analysis, no, we'll do the same stuff, no, constructing the matrix equations as well. Okay. And then we get the results. Another example, no, you can also scan the Python code here. No? So this one is showing how to analyze the truss, no, using only the standard libraries. No? NumPy, Matplotlib, no, and Pandas. No? Actually, no Pandas here. No? NumPy and Matplotlib only. But the end result is this. No? So we can visualize the truss as well as its deformation when we apply loads to it, no, again, as well as those in red, no, as we see that some members are failing, no, in the design. Okay. Next, so I'll run through some of the libraries that we can use, no, use that that use finite element analysis. So here are some of them. No? So I'll focus on these four. So finite, OpenSys, concrete properties, and section properties libraries. No? But there are lots of them. No? Yeah. So for OpenSys, so originally OpenSys was written in C++ as well as Fortran, but it has an interface for TCL programming language. But Scott and others developed an interface, no, so that we can use Python for the OpenSys library. No? So this is now what we call the OpenSys Py library. No? So they created an interpreter for this. No? And then now, from that interpreter, we can call the OpenSys functions. So basically, OpenSys is primarily for earthquake engineering applications. No? So it's developed by PEER, which is an earthquake engineering research center. No? So that's why OpenSys Py library is good for earthquake engineering simulations. No? But you can use it as well for basic analysis of structures. Yeah. So here are the libraries, and here's the documentation. No? So from OpenSys, you can make something like this. Right? So creating a 3D structure and then analyze, or even check the interaction between the structure in the soil, no, the deformations here, as well as the effect on the beam of a moving load, no, as it passes, no, and how it vibrates through time. Yeah. And then a simpler alternative, no, is PyNite. No? So this one, so while OpenSys Py is good for many applications, no, linear and nonlinear analysis, but PyNite is only for linear analysis. No? But nevertheless, PyNite can be used for regular use, no, of structural engineers, no? Because for regular structures, no, standard structures, elastic analysis is fine for use. No? So some examples, no, here, typically, the theory assumes that foundations are rigid, so meaning they do not deform, they only rotate as one. But that assumption is dangerous for very thin foundations. No? And a program in PyNite shows that it's such the case. As we go thicker, the variation in the soil pressure is linear, but if we go thinner, like 250 millimeters thickness, the graph is non-linear. They do not fall on the straight line. No? And the forces there are even larger than the rigid body assumption. No? So best to assume non-linear behavior. No? And then this is one program that I made in using PyNite, no? A design of slabs, no, for reinforcements. No? So actually, I already applied this to one of my projects, no, in the office. Now, there are two more libraries here, so section properties and concrete properties. So basically, these two allows us to do a discretization of the section like rectangles or I-beams, no, if you have SIM1, no, and then do some calculation of geometric properties or even stresses using, of course, finite element analysis as well. And then this one is, of course, for concrete applications. Okay. Now, last is some miscellaneous examples. No? So these examples do not use any of the finite element or proprietary libraries. So this one is getting sections from an Excel file, no, and then use that to design steel beams, no, based on the standards. No. So it uses NumPy and Pandas, as well as tkinter for the GUI, like that. Then this one has some tools for analysis of structures for earthquake, no? And the one on the right is visualizing the occurrence of earthquakes from several years. No? So it uses the Mapbox library to visualize the locations of earthquakes. And then lastly, this one is analysis of columns using design. And so I think that's the end of my presentation. No? So before we end, so I would like to acknowledge these people, no, for making my presentation possible. So my fellow structural engineers as well as organizations. Yeah. So with that, that ends my presentation. Thank you very much and good afternoon.